So first I'll talk a bit about the scales of interest that I'm going to talk about. And then I'll talk a bit about regional modelling of geothermal heat in Northern England. And then if there's time, I might mention a bit about some other work that we're starting to get involved with to do with looking at geothermal energy on smaller scales. So first, what scales am I talking about? Well, to start with, when I'm talking about geothermal heat, I mean heat that comes from the centre of the Earth. So we're not looking at shallow geothermal systems that might use, for instance, ground source heat pumps, where heat is extracted from the solar energy or another source and put underground to store. We're looking at extracting and exploiting the heat that is actually formed within the core and the mantle and the crust of the Earth, to give you a sense of scale. And so we want to look at how this heat is distributed at the surface of the Earth over scales from a few kilometres to hundreds of kilometres. And so what we need to consider are the things shown in this diagram here on the right. We need to consider the different composition of the rocks and how they allow heat to travel through them. Potentially, as we get to smaller scales, we'll need to consider the flow of hydrothermal fluids and how they carry heat. And then if we get very close to the surface, which is a bit too small for us to consider, we'll have to consider radiation effects from the sun. So we're focusing mainly on conduction of heat, as that's the primary driving mechanism for the scales we're looking at. To be a bit more quantitative about this, here are some numbers along the top here, ranging from micrometers up to thousands of kilometers. And we'll be looking at processes at the left-hand side of this scale over here. So most of the work I've been doing in the past year has been focused on trying to create a regional map of the heat beneath Northern England. This has been a project that has been funded by the North East Local Enterprise Partnership, and you can see the outline of their area of interest over there. So it's not a massive area, as you can see. And what they wanted out of the project was they wanted maps of how the temperature varied at depths, say from the surface down to 5 kilometres beneath this region. So they could plan geothermal heating networks for businesses and residents in this area. So to return to this diagram of the scales, we'll be looking at the processes at this end. And in terms of the data that we'll use to help us build a model, we'll also be looking at data that's been collected underground in boreholes. So these are geophysical measurements of temperature, things like the radioactive content or radioactive decay within the rocks made at depth, and also properties of the rocks that can be measured in samples that are brought to the surface as core. And then at a larger scale, in terms of the data we'll be using models that are constructed from 2D and 3D seismic data to make a regional map of the geological structure in the area. Just to put into maths what I was saying earlier, that we're considering processes in which conduction is the primary mechanism of transferring heat. So here in the top equation, we've got the thermal conductivity here, which is isotropic, but varies as a position of space. T is the temperature, and we're also considering production of heat within the rock by radiogenic sources. And this is the only bit of maths I'm going to show in the talk. It's just for a bit of background. And this top equation is often expressed in terms purely of vertical components of transport of heat to the surface, in which this Q here is the heat flow. So this is a simplification of the first equation. So the first thing we did was look at regional work that's done, existing work that's been done within the region to do with geothermal heat flow. And the most obvious thing to do if you want to know the heat underground is obviously to drill a hole and measure the heat, which is what lots of people have done in the past. So we started by reviewing the literature on that. And in fact, this had already been reviewed in the 1980s by the British Geological Survey. And throughout the 80s, there was quite a lot of interest in geothermal energy due to problems with North Sea oil supply. And so there was this effort by the BGS to try and catalogue all known data to do with geothermal heat throughout the UK. And so what they did is that they collated over 1,000 measurements made in different boreholes around the UK. And these have stayed as the benchmark for people's understanding of geothermal heat in the UK ever since. So here are two maps showing interpolations of temperature on the left and of estimated heat flow on the right between these boreholes across the UK. And this temperature is at a depth of 1 kilometre. And as you can see, there's very low spatial resolution in these maps. And there are some very odd features. For instance, these little blue patches here, and the intense shaping of the contours around here is obviously just due to the higher sampling in these regions compared to, say, up here in the north of Scotland. So what was learnt from this compilation of boreholes was that we don't have enough accuracy in the borehole data to be able to map, using a simple interpolation approach, to map the geothermal heat across the whole of the UK. Another approach that people have taken to try and understand heat flow is to look at much larger scales and look at the heat that comes from the mantle into the base of the crust. So here's an example from a paper a couple of years ago, and what this paper did was they looked at the strength of the magnetic field at the Earth's surface, and they estimated something called the Curie depth, which is a depth around which the temperature is around 580 degrees C. And they mapped this depth across the UK, and from that estimated the heat flow between the Curie depth and the surface. And they got this map here on the left. So red colours in the background are areas of higher heat flow, green are areas of lower heat flow. And on the right is the uncertainty in their estimates. And then overlaid on this map on the left are estimates of the heat flow from boreholes that we saw on the previous slide. And as you can see, in certain areas, in fact, I'd say throughout most of this map, there's not a great correlation between the heat flow they estimate that's coming up through the mantle at the base of the crust and the heat flow that's estimated from boreholes at the surface. This is particularly obvious here in northern England and down here in Cornwall and also in the North Sea here. And the reason for that is that this approach is only, it's ignoring any heat that's added in the crust itself. And that's actually a large component of the heat that we extract in geothermal energy, because there's lots of radioactive elements within the Earth's crust that can generate heat. And that's the case in these areas here. There's large bodies of granite, which is very radiogenic. And then finally, a third approach which people have taken, although taken very rarely actually within the UK, to understanding geothermal heat flow is to build a model, a computational model based on the known geological structure. So to take a 3D cube of geological data, to populate it with known properties like thermal conductivity and heat production, and then to run that model by solving the conduction equation and seeing where the heat goes. So here's an example from earlier in this year, which actually fortuitously is looking at the northern region of England here in an area called the Northumberland Solway Trough. Here's a cutaway through the geological model at the top. This red splodge here, that is a body of granite at depth that I mentioned before. The green is what's known as background basement rock. So basically we don't have much information on what it is. And then these layers over here are different sedimentary layers with different properties. And so what these authors did was they built the physics-based model I've described, and they ran it, and they came up with outputs like this. So this is a plot of temperature at a depth of 1 kilometre within this box here on the map. And it's picking up the broad features quite nicely that you can see to some extent in the borehole data. So this red blob here is to do with sediments overlaying some of the granite, and these act as a blanket to trap some of the heat from the granite. The problem with this approach is that it relies on building a model of a best possible description of the structure, and then running one single computational model, which gives you an output like this. So it takes no information, quantitative information from boreholes at the surface or from the observations of heat flow at the mantle at depth. And there's no way of assessing how reliable it is. There's no quantification of error on these models. So what we decided to do was to take these previous three approaches that have been applied to Britain and to build a new type of model, an inverse model where we give inputs of what we think the flow of heat from the mantle is, estimates of heat flow from boreholes at the surface, and also probabilistic estimates of the structure and the composition of the geological layers, and then run this inverse model many times to give a best possible estimate. The first thing we had to do before we could get on to building this model was to reassess the boreholes and the data from the boreholes across the region. So the BGS did their compilation in the 1980s, and that gives a very good overview of the data that's available. But in terms of the details, a lot of the details that are required aren't published within the BGS reports. So I spent quite a lot of time going back through all the old publications and reports. So these range back from the 1860s and 70s, when people first started comprehensively measuring underground temperatures, through academic papers from the 40s onwards. It's also included reports from the oil and gas industry, so that's an example here on the left. And this is part of the BGS catalogue of data here. As you can see, this is a wide variety of different data formats. So it took quite a long time to standardize them and look at all of them. And having done that, here on the right now on the map, what you can see, the red dots, they show boreholes where we have temperatures and thermal conductivities recorded within the boreholes. The yellow dots and triangles show places where we've only got temperature measurements. And the difference in shapes, the triangles are places where we don't have access to the data for various reasons, and the dots are places where we do have access to the data. So if we just focus in on this box here, you can see that the data aren't very well spatially distributed. There's a clustering up here, and quite a lot of the data points shown by these triangles are actually restricted for various reasons, so we can't access them. And also, as you can see, there aren't that many places where we actually have measurements of thermal conductivity as well as temperature, shown by these red dots. So for places where we didn't have measurements of thermal conductivity, we needed a way to map or to estimate thermal conductivity. And we did this by mapping observations of the different rock layers at depth. So these are called stratigraphic columns. There's one shown here on the left. We mapped those into maps of thermal conductivity with depth by using lookup tables, compilations of average thermal conductivity for different rock types. And doing that, this is a flowchart of how we did it. It's not important for this. And here are three different methods that we use. This is an example of a borehole where there was thermal conductivity available. So this is a plot of measured thermal conductivity against depth, down to a depth of around 300 meters on the left-hand side. And then these here are different stratigraphic interpretations and the corresponding estimates of thermal conductivity that we made. And so once we've been through that for our catalogue of different boreholes, for every borehole we now have a profile of temperature against depth and of thermal conductivity against depth. And importantly, these profiles have estimates of the uncertainty in the measurements, which are shown here by the horizontal error bars. And what we want to do with these borehole measurements is estimate the heat flow close to the surface that we can then use as input to our 3D model. And to estimate the heat flow, we also need to understand something about the history of climatological changes in temperature at the surface of the Earth, because these have an influence on temperatures at depth. So here on the right is an example of how the temperature is thought to have varied throughout the last 150,000 years through the last glacial cycles. And I won't go into the details, but by combining these climate records with the records of temperature in the borehole, and by doing some Monte Carlo sampling, some statistical sampling of all the different possible combinations of the uncertainties in all these parameters, we can estimate heat flow in these boreholes. So here's an example from a borehole in Cumbria. This is the data, the original data from 1985, and the authors estimated the heat flow there, which, as you can see, is just one single value with no uncertainty. And on the left-hand side, based on our statistical analysis, we came up with a best estimated heat flow, shown here by this blue curve. This is after the climate corrections have been applied, this blue curve here, of around 63 plus or minus 7 milliwatts per meter squared. So that's good, because now we have a consistent set of values of heat flow across the region that have been estimated using a consistent method and have estimates of their uncertainty. So now we've just been looking at this area over here. And if we return to look at building the 3D model we want to build across this region, just to remind you, this is the geological structure, the model of the region that we'll be using. And the idea is, as I've said, that we can use the borehole heat flow values at the top to calibrate our estimates. And also at the bottom, estimates of heat flow from the mantle. I don't have any results from this model that I can show you now, unfortunately, but this is an example of output from the code that the model will be built with. This is from a paper a couple of years ago. And this is showing heat flow beneath a section of Australia. So here, shown in these blue dots, these are estimates in borehole of the surface heat flow. The red line is an estimate of the surface heat flow from the model. Shown here in this panel is estimated temperatures from the model. And then in this panel and the bottom panel are shown the thermal conductivity and the rate at which heat is produced by radioactivity after the model has been run. So these are the best estimates of all of these parameters for the region. And we want to do this in a 3-dimensional sense beneath this box here. And that's work in progress. And the hope is that using this model, we can build something similar to what is shown here. So this is a site called ThermoGIS from the Netherlands. And they've taken a similar approach to build a 3D model. And then around this model, they've built a web page, which is very interactive. This is just a screenshot, so I can't show you. But you can look at different depths within the Netherlands, and you can look at things like the heat in place, how much power you could expect to get out of it, how economically sensible it is to do that. And this is part of a big effort over the past few years that has helped the Netherlands really make use of a lot of its geothermal energy. So a lot of the greenhouses in the Netherlands, for instance, are now heated using geothermal energy. And this is good news for the UK because the geological setting of the Netherlands is very similar to areas of Eastern England. How long have I spoken for? So I'm been tracking. Oh, it's 2:20. Okay.
If you could wrap it up, that'd be.
Yeah, that's fine. Yeah, sorry. Yeah, I'll stop there then.
Okay, thank you very much, Alex. Have we got any questions from the chat? There's probably only time for one. If not, I have a question sort of pre-lined up about modeling this in 3D. How do you sort of account for boundary effects on your model?
Basically, the boundary is the model is made to be quite a bit bigger than the region we want to look at.
Okay. So if there are no other questions, I'd like to thank Alex for the talk. And yeah, we could move on to the next person.